going to check and see if I can multiply these two things together and rewrite it in terms of a radical. You basically have to follow one very simple rule. If you're going to combine radicals, you have to have the same nth root. Same like you would have if you wanted to combine variables. You have to have the same exponent. Same base, same exponent. These are bases and exponents as well. They're just written differently. They're written in terms of nth roots, not fractional exponents. This first example here is the cube root of 6 times the square root of 2. I cannot put those two underneath the same radical, same nth root, because one of them has a cube root, the other one has a square root. The nth roots are different. One's a 3, one's a 2. Last time I checked, 3 doesn't equal 2. I hope that you are in agreement with me on this one. It's asking a lot, but I'm hoping you're okay with that. I know, isn't it crazy? 3 doesn't equal 2. I know. Okay. So this one, since your exponents or your nth roots, are different, you cannot combine them. So it would just, your answer would have been just that. Now, could you just type it in your calculator and get a decimal? Sure, but what fun is that? I want you to leave it in simplified radical form. But here, with the cube root of -4 times the cube root of 2, do those guys have the same nth root? Yeah. So I can combine them. I can combine them as the cube root of, well, what's -4 times 2? So what's the cube root of -8? And you're done. Okay? So some of these things you can simplify further than you can others. And it works out just like that. Just by working with the nth root.
So you always multiply the numbers?
Yep. Yep. And if they had variables, which they will here in a second, you follow your exponent rules like we did before. So if it was x squared times x to the 5th, same base, different exponents, you add them, it'd be x to the 2nd. We're doing that stuff today, but it's just all going to be mixed in with nth roots. Okay? Same deal here. If I want to simplify, the cube root of 54x to the 5th, why not? So, just like we did before, when you work with square roots, you were looking for perfect squares. So if we were taking a square root, we'd look for perfect squares, which were 1, 4, 9, 16, 25, 36, 49, and so on. Okay? We would look, so if this is the square root of 54, we'd see which one is the biggest perfect square that goes in. But now that it's a cube root, you're looking for the largest perfect cube, which means you have to know what your perfect cube roots are. Well, 1, what's 2 cubed? 3. 4. 5. 125. 6. 220. Which one is it? No, it's only 205. 205. What?
I said that was so funny, I forgot to laugh.
Worth the side eat.
No. Sarah's story.
I didn't say that.
You don't like my Spanish?
I was being obsessed by your comeback.
What's wrong with my Spanish?
Nothing.
What's wrong with my Spanish? ¿Qué pasó mi español? Okay. So, más matemáticas, por favor. Ayúdame. So, es un idiota. Sorry.
I don't know how.
Anyway, so just like we did before, we're looking for perfect cube roots to simplify out. Or later on, you might have a 4th root or a 5th root or something like that. Now, depending upon whether or not I allowed you to have a calculator to do some of these things, it's, if I don't let you have a calculator, I'll try and make sure it's going to be something that's relatively simple to work through versus using the calculator. Do you remember how to do that with the table?
It's whatever number divided. I do not.
Oh, why?
Yeah. So whatever you have, if you
Divided by.
didn't remember how to do it this or the other way, all you have to put in your table is do whatever number, 54, divided by whatever your nth root is. Well, in this case, my nth root is 3, so I would write it as 54 divided by x cubed, and the calculator will look through values that would work out to be a regular old integer here. But knowing this one, this is the same thing as saying 27 times 2 and x to the 5th. Now, I'm going to take this one step further. 27 is what number cubed? 3. It was stuck on the way up, right? So this is the same thing as saying 3 cubed times 2 times x to the 5th. I'm going to use this method a couple of times today by listing out in terms of prime factorization because it helps to see which groupings can come out. So if you think about that, remember that shortcut I showed you yesterday about using the exponents by dividing and what's remainders and stuff? Oh, it'd be helpful. How many times does 3 go into 3? Once, so 1 comes out, does any stay in? No. 2 doesn't work, but how many times does 3 go into 5? How many stay in then? 2. Yeah, you just had it backwards. So 1 comes out, and we leave on the inside a 2x squared. And then you're done. You simplify. You're mixing together a little bit of that, that shortcut stuff we did yesterday when we were just dividing out the exponents and looking for remainders and writing it in terms of some prime factors. Yes, sir? Because what I did was I took out, there was an x cubed. Because this x to the 5th, if I rewrite that, I can write it as this. So 1 comes out, and I have 2 left in. That's what I was doing. I was just saying it without splitting that out.
That makes more sense. Thank you.
So it really isn't any all that different from what we've done before, except there's a cube root instead of a square root. So what do you think is going to happen when you start to multiply them together? Foil? What are you foiling? Do you see a binomial here?
Yes.
So here's what happens. Does everybody agree that these are both the same nth roots? Yeah. So what we do is just write it out. 8 times 6 is x to the 6th, and it's y to the 7th. Okay? Now, perfect fifth roots. Anything above 2 is going to be really, really big. Because if you start to think about it, 3 cubed is already 27. 3 to the 4th is 3 squared, so it's 81. So 3 to the 5th is already way too big. But 2's are easy. 2 squared is 4. 2 to the, then you multiply that with 2, you get 8. So 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. But 2 to the 6th is 64. 32 doesn't go into that cleanly, does it? No. So is there a perfect fifth root that'll work with 48? No. That's the kind of stuff you'll think of. Okay. So that didn't work. So the 48 will stay put, but how many times does 5 go into 7? 1. How many are left over? So how many x's and y's can I take out? 1 of each, and how many are left? That's how it works. And you're done.
Wait, isn't it the fifth root?
Oh, thank you. Sorry, I forgot to put that in there. And that's something that I saw happen with Jolie when Flex, when she was trying to simplify her stuff. She was doing everything right, but what she forgot on the Excel thing, she forgot to put the nth root in, so it was marking it wrong. And I didn't even notice it right away. So that's the one downfall of the computer programs if you start getting into some of the actual forms of assessment with it. Because once you press enter, there's no going back. Like if you're doing it in terms of a quiz or something like that. So if you accidentally do all of your work right, but you forget to put a 5 there, the computer's going to mark it wrong. Whereas if I see it, I'll say, hey, knucklehead, you forgot a 5. But you did everything else right. Am I going to be mad at you? A little, but not like, you know, lots of red ink mad. Okay? Yes, ma'am. You know, the more I thought about it and the more I was asking some of the other teachers that used it, probably not. Because it's too much of a mess. Because of just that, I'd have to do just as much work, and that's not, I mean it's a bad thing that I have to do work. Oh my gosh, it's my job, it's what I do. But I'd have to go back and double check all the calculators, all the stuff on the screens anyway. Why not just do it on paper? Because I can annotate on paper, so we probably won't. I think it's a great idea for homework because it's quick, instantaneous feedback. Hey, what'd you do wrong? You can hit a button and it tells you right away. Oh, forgot to put a 5th root, and so on.
I vote yes to math.
What's that?
I vote yes to math.
And I think it's great for some things. I really do. This stuff, this first part of this chapter is great for it because it's a lot of exponent rules. There's not much variance from that.
I vote yes to that, and I vote no to no class.
So what's going to happen then, do you think, when you start doing division? Use divide rules. Yes. So, hey guys, this doesn't, these rules here this still is going to work because they have the same nth root. So all you do, instead of writing it as 2 separate square roots, make it one giant fraction and go part by part. What's that?
Don't they like cancel out?
What do you mean? The nth roots?
Yeah, so like can you just get rid of it?
No, they don't cancel each other out, but you just make it one giant fraction.
Oh, okay.
That's all it is. Since they're the same nth root, you can do that. If they were different nth roots, could I do anything with the problem? No. Okay? Yeah, there's a baby there.
Oh,
So you have a 48x cubed y squared and a 6x to the 4th and y. So now you do just like you did before. Simplify each part. What's 48 divided by 6? 8. And then you play the game of war. Who wins? X cubed or x to the 4th? So that stays at the bottom. Who wins? Y squared or y? Now, is there anything else I can simplify? The 8. What's the cube root of 8? 2. So my final answer here would be 2 cube root of y over x. We'll take that a step further here in a little bit. Because eventually we're going to say, aside from this part here, from just plain old simplify, eventually I will say something about rationalizing. We'll talk about
so like when you say in a little bit, you mean like tomorrow, or do you mean like later today?
like in about like 4 minutes. So take a second and do this one.
Sarah, you're
You get to that spot, right?
yeah.
So now, what can you simplify? Well, what's the square root of 4/9? 2/3. So you have 2/3. And now you still have in here, now it's a 1 over, well, ab squared. What can you take out? Not the whole thing though, but I take out a b. But where do I have to put it? Numerator or denominator? Denominator. So it becomes 2 over 3b root 1 over a. That's it. Very, very exciting. I hope you find it exciting.
Isn't this how we would plug it in on the math Excel?
Yeah, unless it asks you to rationalize, and that's where we're going to head towards. No, I guess this is too easy. Too easy. Rationalize. Rationalizing the denominator. You did this over and over and over again last year, probably without realizing that you're doing that because you usually press the button. For example, you had that in the denominator a lot of times working with 30, 60, 90 triangles. You had a root 3. Having square roots or nth roots in denominators is not proper mathicate. I just put it together and called it mathicate.
That's unusual.
It is. I made it so. Proper mathicate states that you do not have radicals in your denominators. We get rid of them. So what we do is we multiply when we have we have radicals within denominators, we multiply them by something that gets rid of it. The square root of 3, well, to rationalize that, what we did last year is you multiply it by some factor of 1. Because what's root 3 divided by root 3? 1. It's just written differently. So the square root of 3 times the square root of 3 is 3. That's how I'm able to get rid of that root. So your numerator became root 3 over 3. That was what we called an exact answer. It happened all the time. 30, 60, 90, 45, 45, 90 triangles. It was a very simple thing. But more often than not, you guys were probably pressing buttons on the calculator, and it was telling you, oh, your answer is 2 root 3 over 3. Something like that. Okay? It wasn't terrible. You've also done this with imaginary numbers. Remember when we got rid of imaginary numbers in denominators by doing basically the same thing. You multiplied by some factor of 1 to create, usually created a difference of squares, and FOILed all that out. This is the same basic process. We want to get rid of these roots in the denominator by figuring out some nth root to get rid of them. So it doesn't change, but I want to show you what we did. This is the same as the nth root of 3 to the first. Are we okay with that? I'm writing out with all the exponents and everything so you can see what really happened. Because I think this is a nice shortcut way to show what you're going to be doing via exponents. How many more 3's do I need to make this a 3 squared? One of them. And I can make the same thing here. Because now this becomes same base, different exponents. We add them. That's why that works. The square root of 3 squared is 3. That's why that works. Okay. If this was a 12th root of 3, how many more 3's would I need to multiply it by to make it a 12th? 11 of them. It's the same basic idea. Okay? It's the same basic idea. Why, hello, how are you today? Glad to hear it.
Is it gas?
No. LeBlanc, your car's being towed. And it says by the Pope. Seems really nice. I don't really know him, but it seems cool. Speaks a lot of languages. Artie's looking at me going, what are you talking about? So let's do that and then work through the idea of rationalizing denominators, okay? We have square roots. Excuse me. We're going to simplify out using our square roots, and then we'll see if we have to rationalize anything. What do you think? Can you divide by 0?
No.
So what is the answer?
Error.
No.
Error.
No.
Undefined.
It's undefined. Hey, what's 5.8 divided by negative 1? Yeah, she's yelling through it. Sorry, I didn't hear that. What?
She's like, and you have no friends. She's just kind of like, okay, oh, okay.
She's not a nice lady. So you rewrite this. And just like we did before, you start going bit by bit. What's 18 over 2? And what's x to the 5th over x cubed? X squared. So we wind up with 9x squared. And what's the square root of 9x squared? 3x. Okay. In this case, I didn't have to worry about rationalizing anything. I didn't have anything left in the denominator that was a root. We're good. Okay. Let's see if we can find one. I bet you there's one around here somewhere. What's that?
This is the one I'm having.
Oh yeah, you're already doing your homework? Uh-huh. I need to change the timing on those things for everybody. I can do that, where I can change the time that it's not live for you until like 2:40, 2:30 I can do.
One of the other things
Why
I
not?
haven't noticed that.
And then I can make it shut off at 7:40. Oh yeah, I can do so much stuff with that. I can make you not get unlimited tries to get the answer right.
Oh, no.
Don't do that.
I can get rid of the tab that says ask for help and the little thing tells you what to do. I can do all that.
I'm used to that now.
Oh, yeah.
That you can hear that.
So let's walk through this one. Let's walk through this one. We have the cube root of 5x squared over 12y squared z. And you guys are already mumbling, 5 and 12, they're not divisible at all. There's no cube root that goes into 12. There's obviously no cube root for 5. So this is going to be an example of where we're going to have to try and rationalize to make this work. So the first thing I would do is I'm going to rewrite this in terms of two parts. I'm also going to rewrite it in terms of prime factors. Is 5 a prime? Yes. Is 5 a prime number? Yes. 5. It's just 5 to the first power. You're okay with that? 12 is what written out as factors of primes? It's 2, 2, and 3, right? So it's 2 squared, 3 to the first. You okay with that? So I'm going to write it out in terms of exponents. 2 squared, 3 to the first, y squared, and z to the first. Do you see why I'm doing it that way? Because now I can see how many more of each one of those exponents I need to create a 3, a factor of 3. Okay? That's the trick. It's a real simple thing to do. It's just a matter of remembering how to prime factor. Okay? That's how it goes. Okay. So how many more 2's do I need? I need one of them, right? How many 3's do I need? 2 of them. Y's and Z's. And this is in cube here. And then what do I put in the numerator then? The exact same thing. Because it's still the same amount above one another, so when you divide it, it's still a factor of 1. It just looks like crap. That's all. By working through these prime factor ideas, by using your exponents, it just creates, you're creating perfect cube roots underneath the radical. Perfect end roots. So we have a cube root, 2. So if I do that, I'm going to write that below here. My denominator becomes, can I move this up just a little bit? Are we okay? It doesn't really cut it off, so whatever. My denominator becomes now the cube root of 2 cubed, 3 cubed, y cubed, and z cubed. Now, let's just say, for argument's sake, that this was a 2 to the 4th power. Bless you. How many more would I have put in? 2 more. I would put 2, that way it gets to the next multiple of 3. Does that make sense? You're trying to get to multiples of 3. It's not always just going to be below the value, it can be above. So if it was 2 to the 7th, I'd have to add 2 more of them again to the 9th, so that way I can take out 3. Little subtleties like that. Numerator, I get cube root of a bunch of stuff being multiplied together. 5, 2, a 3 squared, an x squared, a y, and a z squared. All I'm doing is putting all my numbers first. So what's 5 times 2? Bless you. What's 3 squared? So 5 times 9 is 90. Oh, sorry, 10 times 90, thank you. Oh, before I go there, these guys all have these have exponents of 1, and that has an exponent of 2. Will there be a perfect cube root within those prime numbers? No. The reason there's no perfect cube because none of them have a cube root. So I can go ahead and multiply all that out and know that I can't simplify it any further. So my final answer here is going to be the cube root of 90, x squared y z squared, and then denominator, and I'm going to do no again, don't worry. My denominator, see how all these exponents basically cancel each other out? So I get 2 times 3 times y times z, which is 6yz. Okay? Remember, what you're trying to do is you're trying to create the exponents to be divisible by your nth root. That's all you're doing. And just by adding these things together. We started with 12. 12 factors to 4 and 3, which is 2, 2, and 3. So 2 squared, 3 in the first. Prime factor it, and then how many more do you have to put together?
I got all of that.
Oh, the 5 was already up here, Dan. That was already the numerator. Since I had to multiply these guys together.
Okay, that makes so much more sense.
I said, oh, that's just, and so there would be a
Why
5.
did they throw a 5 in there?
Just for fun. You know, why not? Sure, you want to know? I know what it is. This one's actually a little bit easier because the denominator is not a composite. Yes, solve for question mark. Simplify it, rationalize your denominator, okay? How? So we did. All right, let's see what we did. So bottom one here, it's already, 5's a prime number. How many more do you have to multiply by to get to a cube? 2 of them. So we have a 5 squared and a y. So you get 5y in the denominator. And 5 squared is how much? So 7 quarters is how much money? Go. And you're done. That's how you rationalize it. I'm pretty sure it's not 60. I know how to count money. Well,
Wait, can you go back up?
what do you think you're gonna have to do here? No? You've done this problem before.
Why? Wait.
You did this problem before. You did this problem as an imaginary. If it was 1 minus I, you'd have to multiply it by 1 plus I. You'd multiply by what's called the conjugate. It's the exact same thing here. Instead of an imaginary number, you're multiplying by a root. What's the conjugate of 1 minus 2i, or 1 minus root 2? 1 plus root 2. Isn't that a difference of squares? You get 1 minus root 2 squared. 1 minus 2. And this is where we get to more and more tomorrow. Okay? Math Excel stuff is already uploaded, and you'll be able to go through it. Okay? What's that?
Is that on tonight's one?
I don't think so.
Okay.
Yes, ma'am.
I'm not gonna worry about it.